Our next speaker is Marko. The title is Detecting and Explaining Inequivalence of Context-Free Grammars. So Marko, can you hear us?
Yes, I can.
Yes, please, go ahead.
Thank you for the introduction. Hi, I'm Marko, and I'm a PhD student at Ruhr University in Bochum, Germany. And yeah, there, my team and I develop a tutoring system for students. And now our paper is about detecting and explaining inequivalence of context-free grammars. All right, let's jump right into it. A typical exercise you would pose in theory courses, bachelor theory courses, you probably have seen them in your own courses as well, is, let's just have this figured out. Sorry about that. Yeah, there we go. All right. We have this task which asks students to provide a context-free grammar for the language that is given right there. And, well, the question is, what should the system answer now? We would like the system to give feedback on this task. And what we ideally would like to have is that the system can determine the correctness, like is the grammar correct, and also to give some feedback and explanation on mistakes, like pinpoint the mistakes. For example, we would expect feedback. Well, your language describes, or the grammar you provided describes the word AAB, but that's not in the language you should describe. Or even on a higher level, which is more interesting, that we can provide the language that the student have modeled by their grammar, or even tell them, oh, well, look at this specific rule, this might help you to solve your problem. So that's our main goal, give high-level feedback that really tells the student something about their mistake. Well, and that is difficult, because, well, even deciding the equivalence of context-free grammars is undecidable, so providing this feedback is even more challenging. So, what can we do? Our framework offers a solution to that. We combine several factors to provide this kind of feedback. Of course, not in all cases, we would solve an undecidable problem, but in many cases. So we use grammar transformations, we use a subclass of context-free languages and algorithms for that subclass, and also a grammar canonization method. And this talk, I'm going to first give you a glimpse into our framework and tell you something about it, and then also give you a very little peek on how we evaluated it on Relay later. Great. So first, let's focus on the feedback of the type. You might look at this production because that might help you figure out what you did there. For this, we use transformations. And before I look into this specific feedback or this explanation, let's first look into how to determine correctness of a grammar by using transformations. Right. We use equivalence transformations on grammars. They can be as simple as we remove unnecessary non-terminals, like non-producing or non-generating, for example. But it can also be like a little bit more advanced and non-standard things, like here getting rid of one reduction level, which is not necessary. That's an example on the slides. And to be flexible, to specify these transformations and also specify them in the descriptive way, we designed a new transformation language and call them pattern-based transformations. They use the style of, we have patterns, like we basically replace non-terminals by pattern variables and offer some syntactic sugar on that to be able to specify transformations in a nice way. Now, for testing equivalence, our procedure is to design a pipeline. We designed a pipeline for normalizing grammars, like a pipeline which like pipelines all these transformations together, and they don't have to be that linear, but instead the result of such a grammar can also be multiple grammars, because the transformation can be the application can be non-deterministic. Yeah. So yeah, right. Let's go ahead. Now, if you have this pipeline and this normalization method, to when a student comes in and we want to figure out whether it's equivalent, we can normalize both the student attempt with our pipeline and the solution with the pipeline again independently, and then check whether the solution sets we have, whether they match. So if there's a one match, then we know, okay, we can transform the grammars equivalently from this end and from this end. So the student attempt has to be correct, that is equivalent to the solution. Now, if you want to generate hints, like tell them, that's what you did wrong, look at this rule, then we can use non-equivalence transformations. We call them bug-fixing transformations. Our goal, and these bug-fixing transformations describe corrections of typical student errors. So our goal is to apply such a transformation, and now if you apply it to a student submission and get a correct grammar, we know that our transformation actually fixed that error, so we kind of have an idea what the students did wrong here. And then we can return that part of the grammar that we changed as like, that's where the error lies. At least that's one way of describing where the error lies. There might be other ways as well. Yes, okay. That was the very short description of the normalization framework, about transformation framework. Now let's jump into another perspective, and that's providing feedback of the kind, well, you actually modeled this language, but you should model a different one. For this, we use bounded languages. A little definition what they are. Well, a language is bounded if it has a fixed structure, or like if every word has a fixed structure. More formally, language is bounded if there are words such that every word of the language is a repetition of these words in a fixed order. Like every word consists of the same blocks, and only the number of repetitions of the blocks differs. For example, and these words, these blocks, is called the boundedness witness. For example, the language a to the m, ab to the m is bounded because it has the bounded witness a and ab. Great. So why is this class useful for us? Well, it's useful because it has useful properties, and I'll show you two of them. Given any arbitrary conditional grammar, it is decidable, and even in polynomial time decidable, whether it is bounded for any witness. And if I have a witness, I can also test it against this specific witness and tell it whether it's bounded concerning this specific witness. And even more important, or more interesting to us, the equivalence problem is decidable as soon as one of the given grammars is bounded. That was proven in like 1964 already. It was a non-constructive proof. We had to figure out how to put that into an algorithm. But yeah, that's very nice property, because that enables us to use this kind of algorithm as sketched here on the slide. So to provide such a feedback, first we check whether the solution, the student submission is bounded by the same witness as the solution. So whether they have the same structure, all words have the same structure. If that's not the case, well, we can tell the student directly, well, your grammar describes words that don't follow the structure. But if that's fine, then we make sure to use distinct symbols for the different blocks. For example, I go back to slides. In the example here, we have A and AB. So they are not disjunct. The A is present in both. So when we use now individual symbols for them, then we can use the paric image to describe how often the blocks appear. And that's exactly what we want. So we can represent the paric image then as an extensional Pressburg formula. And having that, we can either test for equivalence by just testing for equivalence for these Pressburger formulas, or use the formula to provide a set notation of this language the student modeled. So the structure is the left-hand side of the set notation, and the Pressburger formula is basically the right-hand side. Now I showed you two main aspects of our system, and now it's time to build that all together. I give you an overview how this all interacts in one framework. Let's start with the normalization we've seen in the beginning. With that, we can check whether a grammar can be transformed into a grammar which is where we already know the correctness or the incorrectness. And we also looked at the bug fixing transformations and saw that they can be used to generate more feedback. Yes. Let's now look at these more basic tests, like testing for counterexamples, as many systems actually do. You can easily test for emptiness, like whether the language the student modeled is empty, and then give feedback if the language is not supposed to be empty. Same for finiteness. And by just looking at the paric image, we can also give feedback on the symbol frequency. Like, for example, your language should, or your grammar should describe a language which has, where all words have twice as many A's as B's, but in your language, it's twice as many B's as A's, for example. We also looked at bounded languages. There we can test whether the solution and the student submission are bounded by the same witness, and if so, also test for equivalence. And if all that fails, if it's not a bounded language, if none of the methods for all target languages work, then we don't have a decision. Then an instructor has to do that manually. A central component of our system also is caching. That is, we also not just cache every attempt, but we make sure to cache canonizations of the grammars. That is, we make sure to, it's basically the same thing as graph canonization, where you look for a unified naming of the nodes. Here it's unified naming of the non-terminals that makes sure we don't cache the structurally same grammar twice. Yes, that's our framework. And now just very quickly look on the evaluation on real data.
Can you wrap up in 1 minute?
I can. We evaluated our data on 3 datasets collected in 2 tutoring systems. So in total, we had 55,000 attempts. And what I will show you here is in how many cases we could discover the equivalence. And that is, for these 55,000 attempts, we only had to look at 260 single cluster, that is 260 attempts, that's about 4%. And in many exercises, we didn't have any attempts that our system couldn't evaluate on its own. Yes, so we developed this framework and evaluated it on real data. It is integrated in a real educational support system, ILTIS, where we use it for 2 semesters now. And yeah, thanks for your attention. I'm happy to answer any questions.
Unfortunately, we don't have any time for questions. I hope that you contact the author offline or ask questions on Discord. Let's thank the speaker.